Alright, thermal analysis module in SolidWorks Simulation Professional allows you to calculate heat dissipation through your assemblies, and it takes into account multiple modes of heat transfer. So even though you can apply an thermal load as a boundary condition in static analysis, linear static analysis, which is available under simulation standard, it does not allow you to calculate uh, the heat dissipation through the model. Essentially, it only calculates the thermal stress and thermal expansion, but it doesn't calculate the heat dissipation through your model. So during this webinar, I'm mainly focusing on these sub topics, modes of heat transfer, boundary conditions we can use during the setup, and also the assumptions we will be making, we'll have to make in the simulation professional modules thermal analysis before we conclude the results, and what different types of thermal analysis you could do, and also how can you use the thermal analysis results in other types of analysis in SolidWorks simulation suite. Right. So first of all, let's have a look at some common modes of heat transfer. So primarily there are three types: conduction, convection, and radiation. To give a brief introduction to each one of these, conduction essentially takes place between two bodies, essentially two solid bodies, and generally the heat transfer takes place from hot region to a cooler region. So energy gets transferred from the hotter region to the colder region. And the rate of heat transfer is primarily decided by the material properties. So it's quite crucial that you get your material properties from a reliable source before you set it up, so that you can approximate a realistic output from the simulation module, the calculation. Right. So later on I'll be focusing more on those specific material properties, and let you know how does each one of those matter and how to select each properties to be entered into the database before you create a new custom material. Right. So the second type of heat conduction, heat transfer is convection. So mainly convection takes place between an solid surface or an gaseous surface with an adjacent fluid surface. So basically, if you have a solid component which is undergoing a heat load, which is undertaking a heat load, if it's exposed to an adjacent fluid domain which is in motion, heat gets transferred through convection. So when it comes to convection, primarily there are two types of convections. The first one is called natural convection, and the next one is forced convection. So natural convection is primarily due to, again, the material properties of the adjacent fluid. So for example, as the image indicates, if you have a solid surface at a certain temperature, the air membrane or the fluid membrane adjacent to it gets warmer due to the heat transfer through convection. So as any material gets warmer, it tends to expand and becomes less denser. So the warmer fluid rises up in the air domain or the fluid domain due to the less density, and then it gets replaced by cold air, which is more dense. So this actually establishes some sort of an air current cycle. And again, the direction of warmer fluid motion is against the direction of gravity, and this is considered to be a phenomenon called natural convection. So in SolidWorks simulation professional module, it uses finite element technique, and you can simply study solid bodies with different material properties, but it does not take into account the fluid motion. Therefore, these natural convection currents cannot be simulated during the simulation professional setup. So basically, you have to make use of flow simulation module to understand the behavior of air currents or the fluid currents, but still the effect of natural convection can be taken into account by using a heat transfer coefficient. So later I'll be explaining to you how to decide what value to be used and how to approximate it rather. So the second type of convection is forced convection. So in most cases, in most engineering applications, when we need to cool down a certain surface or a certain body, we make use of fan or a forced airflow or a heat pipe or a liquid flow, let's say a liquid cooling system, etc. So what this does is it actually complements the natural convection system, and it increases the energy transfer rate from the solid surface. So basically, as I told you before, uh, in simulation professional suit, thermal analysis module does not have the functionality to calculate or simulate fluid currents, but it can take into account the effect of fluid currents in terms of a heat transfer coefficient. So to make things slightly easier for you, SolidWorks has provided some experimental data to be used to simulate this sort of scenario. To give you an example, if you approximate or assume your models which you study are undergoing only natural convection, you could use a heat transfer coefficient value between 5 to 25. So why there is a range of values? So basically, sometimes the model you study could be located inside an enclosed chamber, something like an computer CPU or computer casing. Therefore, the air domain is quite confined and it's not as large as it's compared to the situation where the component is completely exposed to air, as in it's sitting outside exposed to an infinite amount of fluid domain. Therefore, you could use values ranging from 5 to 25. So when your air domain is confined and there's not much fluid motion, you could use a lower value where you assume the heat transfer coefficient is low, the heat transfer rate is low. But if it's in an infinitely large air domain, you could use a higher natural convection value, such as 25. It could be applied to other situations as well. So for example, if it's being fan cooled or water cooled, you could use a larger heat transfer coefficient value. So larger the value, the assumption is a higher the rate of heat transfer from your solid surface. Right. So the third type of heat transfer is radiation. So radiation heat transfer does not need a mode or medium to travel. So this is, of course, energy emission by bodies due to their temperature in forms of electromagnetic waves. So every component which has a temperature above absolute zero, they necessarily emit a certain amount of thermal energy, and that goes out in terms of radiation. So radiation effects become significantly higher if your components undergo a large amount of heat energy or at high temperatures. Right, so these effects can be easily simulated using simulation professional thermal analysis, and I'll be showing you an example shortly. Right. So the next thing we have to take into account is conductance. But before I describe conductance, let's have a look at a standard setup, and I'll explain to you how conductance can be taken into account and why is it important that we input conductance into our study setup. So let me quickly open up my SolidWorks model. Right. So here I have chosen a very simple model to demonstrate to you the basic boundary conditions and setup. And just to describe the model itself, this is supposed to be a microchip, and it has a very small heat sink which is made of copper. And the microchip itself is made of, we are assuming it's made of porcelain or ceramic, and there are 3 connectors joined to it. So ideally, this component is located within an electronic enclosure, and most likely we will have a fan which induces a natural convection current which runs through the system, and the heat sink is ideally exposed to it. So setting up a simulation study for thermal analysis is pretty simple. You just enable your simulation add-in in SolidWorks. So if you have a SolidWorks simulation professional license, you will be able to access several other study types apart from static analysis. So thermal analysis is one of them. And the moment you select it, it'll give you the simulation feature tree, which is common throughout all the simulation studies you do in SolidWorks. So if you expand the first folder, it shows you all the parts in your assembly, and it would inherit the properties from the assembly material properties directly. And if you have a look at the material properties in detail, I'm going to right click on one of them and go to the standard library. You would notice now SolidWorks has a color coordinator. It actually color um, it uses a different legend to identify what are the most important properties for a thermal analysis. Okay, notice that two of the properties are in red, mass density and thermal conductivity. One of the properties are in blue and the others are in black. If you go to the normal SolidWorks CAD environment and if you access the material properties, you'll notice everything is in black. Okay, so this means something. So those of you who have done the uh, basic training for simulation would really know. I would assume you would know what it means, the colors mean, but I'll explain to the rest who hasn't gotten the chance to study it. So basically, when you go to a simulation environment, based on the type of study you define. Let's assume I'm creating a static analysis, linear static analysis for stress distribution and displacement analysis. So if I have a look at the material properties within a linear static analysis, notice now it colors elastic modulus, Poisson's ratio, mass density, and yield strength in red, and few others in blue, and others are in black. So this means that for a linear static analysis, the solver uses only these properties, which are colored in red. So if I go to my thermal study and have a look at its material properties, notice only mass density, thermal conductivity, and specific heat are the only properties which are being used. So the meaning of blue and red is the red properties are the mandatory properties to run a basic level thermal analysis. And based on the type of study you do, let's say if you want to do a transient analysis, time-dependent analysis, you may require to key in specific heat. This is not a mandatory property, but if you do a transient analysis, then you need this property. And the ones in black are not being used for this type of study. So that's what the colors mean. Right. Okay, so in our case, we happen to have all the properties defined under the standard library, but only time these come into picture or the importance of these colors will be quite crucial whenever you create your own custom material. For example, if you study a part which is made of a material which is not in the standard library, obviously you'll have to get the properties from some engineering literature or a material database online. So these three properties will be the properties you need to extract, and you'll have to ensure it comes from reliable source. Right, so let's go back to our study and let's actually start defining our boundary conditions. So in a thermal analysis, the only degree of freedom which is being calculated is the temperature, the heat value for each node. So what we have to do first is we have to specify what each component is made of, which we have already done. Next, we have to specify how they are associated to each other, how well they are bonded. So as opposed to an linear static analysis, in an thermal analysis, the only time the contacts come into the picture is to decide whether these two components conduct heat perfectly or whether they are insulated. So if you select insulated, what's going to happen is each one of the contact faces between these components are considered to be perfectly insulated. There won't be any heat conductance between any one of them. But if you select this option bonded, what's going to happen is the software is going to assume each one of these components conduct heat perfectly between each other without losing any. There's no thermal resistance at all. But in a realistic case, that's not the scenario. So we have to take into account a certain amount of thermal resistance. So if we have a look at the exploded view for this assembly, so this is going to be the contact surface between my microchip and the heatsink. So in reality, these surfaces have certain amount of roughness. So due to the presence of surface roughness, there are micro level air pockets or gaps between these two surfaces because they are not perfectly coincident to each other in real life. So therefore, due to the presence of these air gaps, it induces certain amount of thermal resistance. So there won't be perfect conductance between the two. So in electronics industry, we tend to use thermal glue to enhance the conductivity between two components whenever we join two components together. But none of the thermal glues you use are perfectly conducting the heat through. So you have to take into account the thermal conductivity of the material which is being used to bond these two components together. So some examples are given in the SolidWorks Simulation Professional Manual, which you could use. For example, if the contacting phases or the thermal glue you use is made of materials iron or aluminum, the value conductance value you use is around 45,000 watts per meter squared Kelvin. And for other materials, they are given some examples as well. So based on this, you can calculate how much heat resistance is going to be there between the two parts. So ideally, to calculate the heat resistance, you have to take the inverse of these values. Right? Let's go back to our study. So what I'm going to do in this case is I'm going to specify a thermal resistance between these two surfaces. I'm assuming it's bonded using Arctic silver, and right click on connections, go to contact sets, and here you can specify it's going to be a thermal resistance between the two surfaces, and I'm going to put in a distributed value of 2.86 into 10 to the power minus 6. That's going to be my thermal resistance. So it's pretty minimum due to the type of thermal glue I use. So this is not mandatory. You can even run a study without applying thermal resistance. But if you don't apply any, the software will assume it's going to perfectly conduct heat between the two components, which will be somewhat unrealistic. Okay, but it's not mandatory to put this in, but it's good to have it in order to get a realistic result out. So that is done. So let's collapse the assembly. Right. So the next is I need to specify what's the current heat load in my model. So this is microchip. I'm assuming it's operating at a certain power rating, but the entire power consumed by this microchip is not lost as heat power. So essentially, the heat generated by a microchip is a byproduct. It's a somewhat wasted energy. So you always need to find out the efficiency of the microchip and find out what percentage of energy is lost as heat, and that could be used to calculate the heat power generated. That as a rule of thumb. So I'm going to apply a thermal load in this case, and you could either apply a temperature or a heat power onto the microchip. So I'm going to put a heat power in this case, and I'm assuming it's going to generate, let's say, 25 watts of heat. So you could either select a surface or an edge or a vertex to apply heat power, but in this case I'm assuming the entire volume of this microchip is generating heat. So from the feature tree you can easily select your microchip itself, or you could even enable your body selection filter and then click on the right respective body. Okay, so I'm going to put in 25 watts of heat power onto this microchip and accept it. Right, so that is done. So my heat generation rate is applied and contact sets are done, material properties are done. I need to specify how heat gets transferred to the surrounding. So basically I'm assuming this microchip works in an environment where there's a certain amount of forced convection taking place. Let's assume there's a fan acting on the heat sink, helping it to dissipate heat out, and even the microchip is exposed to a certain amount of air, but not as much as the heat sink. So what I'm going to do is I'm going to simply right click on my thermal loads, and I'm going to apply a convection coefficient onto the exposed faces. So when you select it, there's a tool which you could use to easily select all exposed faces in one go. But since I want to apply different convection rates to different parts, I can't use that option. So what I'm going to do is I'm going to first select all the faces from my heat sink. Select all of them quickly. And those two as well. And let me select these ones as well. That's fine. And apply a value of, let's say, 250. I'm assuming it's forced convection. And one more thing you have to specify is the bulk ambient temperature, as in the ambient temperature of the surrounding. So I'm going to assume it's around 300 degrees Kelvin. Again, around 24 degrees Celsius room temperature. Right. So that is done. I'm going to click OK. So one word of advice is if your computer does not have a professional graphics card and if it doesn't have much computational power, always hide these symbols. You could right click on the convection coefficient and click on hide. So although the property is there, it simply hides the symbols. Another shortcut you could use is display show items, and you could select view simulation symbol, so it'll help you to hide everything in one go. So the reason why I ask you to do that is if your assembly is quite complex, the presence of these symbols, each individual cone, it could really slow down your assembly performance. So it could induce a lag. You won't be able to rotate the model properly if your computer does not have enough computational power. So it's always best that you specify the boundary condition appropriately and simply hide it, okay, so that it won't slow down your machine unnecessarily. So I'm going to put in a few more convection surfaces on the microchip itself. So select it, click on each one of the surfaces which are exposed, and here the assumption is the heat dissipated out by this microchip is not as great as what is done by the heat sink. So I'm going to use a lower value there, let's say around 100 watts per meter squared Kelvin. And again, the bulk ambient temperature is 300 degrees Kelvin. Click OK. Right. So boundary conditions are done as well. And my contact conditions materials are specified. Obviously, there won't be any fixtures in my case, and because it doesn't matter. The next thing I want to do is I need to mesh my model. So it's best that you have at least 2 layers of elements across the minimum thickness of your model. So for example, in this case, the thickness of my heat sink is about 2 millimeters. So I could go to mesh, create mesh, and probably create a standard mesh with 1 millimeter overall size. Yeah, as a rule of thumb, you could use that so you can get a proper temperature gradient through the thickness. So at least have 2 layers of high quality elements. So you have 5 nodes across the thickness. All right. So that's pretty much done. And then I can go ahead and run the study. So to save some time, I have already completed the study. And from this analysis, what we did was we are getting the software to calculate what is the steady state temperature, as in the final equilibrium temperature when there is no temperature fluctuation taking place in my model. So essentially, heat power of 25 watts is being generated in this microchip, and the heat's being transferred in or out based on the convection coefficients I have specified. And from the results, I could obtain what's my temperature distribution. Okay, so you'd see something like that first. Let me actually enable my heat plot. I'll turn off the, yeah, there you go. So first of all, you'll see something like that. It'll give you the temperature distribution throughout your model. And you could discretize this further to understand the characteristics of your model better. So for example, if I want to find out what's the temperature through the cross section, I could use the standard plot tools. For example, I could right click on my thermal plot and activate section clipping and select a reference plane from my feature tree. So I'll probably select my right plane, and it would show me the temperature distribution through the cross section. I can even use the probe tool to find out what each heat value is from those nodes. That's another tool I could use. So all the standard plot tools can be used for thermal plots as well. And there are a few more we could use. For example, if I want to find out how well is my model dissipating heat out, and what are the locations or the geometries which contribute to the highest amount of heat dissipation, I could enable something like heat flux. So if I go to my results folder, go to define thermal plot, I could say I want to see the heat flux, the resultant. That's the rate of heat transfer, and click OK. So it indicates to me that which geometries or which parts of my model is contributing to the highest amount of heat transfer. So from that, I can see these cutouts in the heat sink is the most efficient regions when it comes to transferring the heat out, and I can see there isn't much heat being transferred out from these surfaces of the microchip or the connectors. Right, these are some of the result analysis tools you have, or processing tools you have under simulation professional thermal analysis module. And sometimes it could be that you are interested in getting a certain numeric value out. So for example, I want to find out what's the total amount of energy in and out from this surface, the heat energy. So if that's the result you need, you could right click on the results plot again and go to list thermal, list heat power. List heat power. And what that does is it allows you to select the unit you need first. For example, I want to find my result in watts. And then you could select the surface you need to analyze and click on update. So from that you can get an idea what's the total power out, total amount of heat power which is being dissipated from that surface. So for example, if you were to introduce more fins or cutouts in this surface or part, you could actually compare the results between two different studies as well to find out what's the best configuration for your heat sink. So that's one possible application of it. Okay. And some of you might wonder what this list thermal is. So for certain instances, you need to pull out results from each node. So this tool allows you to specify what result component you need, for example, temperature. And when you click OK, what it does is it'll actually pull out the heat values from each and every node, which is of course not very useful at this stage. And if you want to find out results from each node, I'll recommend you getting a temperature plot and use a probe to pull out the results from a certain nodal location. I guess that's one tool you could use. All right. So what we did now was a steady state analysis, which is useful. But at times you might need to study or analyze what's the temperature variation across a period of time, a certain duration. Essentially, you want to apply heat power for a certain period of time and want to find out how long it takes a certain components to heat up to a certain value. So for that, you have to do another type of a thermal analysis called transient analysis. So defining a transient analysis is easy. All you have to do is simply go to your study properties and go to options, and here you specify the type of study you want to do. All right. So before defining a transient analysis, what I'm going to do is I'm also going to define something called a sensor. So ideally, I want to find out the heat results or the temperature values from this point of my assembly. So it could be any point. Just to give you as an example, I want to select that point, that vertex, and I'm interested in the temperature value over there. So I could specify a sensor to record values from that point. So all I have to do is go to the sensors folder in your SolidWorks assembly and go to add sensor, specify that you want to record simulation data, and I want to get thermal results, maybe temperature in Celsius. And I could either say get results from the overall model, or I want to see the maximum over selected entities, that is this vertex, and I want to see the transient results. Right, click OK to that. What it does is it creates a sensor which is linked to thermal information from that specific point. So this sensor can be used in any study as long as it's transient. So what I'm going to do is I'm going to show you how to define a transient analysis. Again, it's similar to how we defined a thermal analysis before. Go to new study, define a thermal analysis, and here under the study properties, you can specify that you want to do a transient analysis. Say I want to study this model for 300 seconds, and you could specify the time step size as well. So smaller the step size, larger your results file would be, longer it takes to calculate. So I'm going to specify a reasonably large step size, around 10 seconds. So altogether there'll be like 30 steps. You could even import the initial temperatures from a previous thermal analysis you have done, but in this case I want to do it from scratch. So I'm simply going to say OK. And if the study properties or setup is common to something you have done before, a thermal analysis you have done before, you could even drag and drop boundary conditions from one thermal study to the other. For example, if I want to get all the study properties from my thermal 5. That's the last steady state analysis I did onto thermal 6. I could simply right click on my paths, connections, and also thermal loads, even the mesh, drag and drop them onto my thermal 6. Click OK. It'll tell you a warning advising us to remesh if any contact conditions are different. So notice all the boundary conditions got copied, and you have to do one extra step in a transient analysis. So the previous analysis we did was steady state. Therefore, the software only tells us the last or the final temperature result or the equilibrium temperature result. It does not actually give us any information about the temperature variation. But now what we are doing is we are starting from 0 and we want to find out how the model would heat up based on an applied heat power. So one extra component we have to define in this case is temperature, or in other words, the initial temperature, what's the starting value. So I'm going to select the entire assembly from the feature tree, and I could apply a starting heat value of 300 degrees Kelvin. All right, so once I've applied that, it's good to go. I can simply run it. So thermal analysis in transient mode takes relatively longer to run compared to a steady state analysis due to the amount of time steps you have. So I'm going to show you the final result which got created. And one critical step is under result options, you can actually specify make use of your sensor. If you don't use this step, you will not be able to use the sensor for your result analysis. So make sure under result options you select your data sensor and specify that you want to record results for all solution steps onto that sensor point. Right, so let's see how that works when I go back to my transient analysis. So this is identical to what you have defined there, and here the result you get is same as before, but notice you see a bit of extra information. It tells you what the time step is and the respective time value. So I'm at step 1, it's 10 seconds. So if I want to see what's going to happen at 30 seconds, I could double click on my plot information, or I could right click on the legend and go to edit definition and specify what the time step I need. So I could say I want to see the result at 30 seconds. Click OK. It shows you the heat result at 30 seconds. If I want to see an animation, right click on the thermal plot, click on animate. It shows you an animation of how the component would get heated up. You could even make use of probe. So for example, if I want to probe a certain point from my cross section and I want to find out how well that gets heated up in time domain. So in steady state analysis, you get one fixed value which is coming from the steady state time step. But in transient analysis, you'll get this extra button which gives you the response in time domain. So the moment you click on it, you will be able to see a graph like that, and it shows you where it starts from. In this our case, it starts at 80 degrees Celsius, and it simply reaches the steady state after a certain amount of time. Let's say after about 189 seconds. Right? And also, how do we use our sensor? So since we have linked that specific point to the sensor, all we have to do is go to your feature tree and move the mouse cursor onto the sensor, and it shows you a preview of the graph. There you go. So it actually shows you, it records the information and will present you the result without you having to probe individual points. So you can have multiple sensors at multiple critical locations so that it captures the information without you having to manually probe them. Right. So that was about using a sensor to capture the transient or time dependent information from your simulation study. Right. So I want to take it a step further. So from my steady state analysis, I know my assembly is going to heat up to this level. So what could this do when it comes to my other mechanical properties? So for example, how much would be the stress caused, or the thermal stress due to this microchip being this hot? So for example, this microchip is going to cause the heat sink to expand in a certain way because it's made of copper, and the microchip itself is going to expand at a different rate. So how is this different rates of expansion going to affect the bonded region, whether the thermal glue is able to sustain this kind of a thermal expansion, and if it would come apart, it would tear apart. So that sort of thing can be studied by transferring this thermal information into a static analysis. So all you have to do in this case is go to your simulation tab, define a new study. Say you want to do a static analysis. All the material properties are automatically inherited from the assembly. If not, you can individually specify it. And under the study properties, you specify that you want to import thermal effects from a thermal study which you have done. So it could either be from a flow simulation study if you have completed one of them, or it could be from one of the existing thermal analysis studies. So I'm going to say I want to bring in temperatures from my steady state analysis, the first one I did. It could even be from a transient analysis, and you can even specify the respective time step. And afterwards, you also have to say what's the reference temperature at zero strain, as in when there is no expansion at all, when the metal and the other solid components are at a neutral level, what's the reference temperature? So this temperature is then compared with the temperatures from thermal study. The software finds out the temperature gradient or change in temperature, and it gets utilized together with the material properties. So every material, almost every material in the SolidWorks database comes with this thermal expansion coefficient. It actually tells you how much it expands or shrinks per Kelvin, per degree Kelvin. So that heat gradient which gets calculated from your thermal results then will get used with thermal expansion coefficient, and the software is able to calculate the respective displacement for each one of the nodes and subsequently showing you the results. So if I have a look at my static analysis which I completed, that's something which you will obtain. Notice I don't have any fixtures. I don't have to define any fixtures. But when you don't define any fixtures, there could be a certain amount of unbalanced forces in your mesh causing rigid body motion. So you always have to make use of soft springs to stabilize the model. Okay, so this is something which is covered under the basic simulation training. What this tool does is whenever there are minor unbalanced forces which are negligible, they could be filtered out using this option in order to avoid rigid body motions. Okay, so in this case I cannot actually use fixtures because I'm not sure where it's going to get fixed. All I want to do is find the resultant deformation due to the thermal distribution or heat distribution throughout the model. So those values were imported using this tool here, import flow thermal effects, and then the software calculated how much stress is it going to induce on my model. So again, you can have a look at the cross-sectional stresses, section clipping, use my right plane, and also you could use it together with your exploded views. So if I explode my assembly, it shows me a certain region which is undergoing stress. I could even find out the shear stress in, let's say, Z direction, and find out what's the value the assembly has to sustain, and subsequently decide what kind of epoxy or any thermal glue I have to use in order to bond them together. So these are some ways of utilizing your thermal study results in order to optimize your model further. You can use it together with your static analysis module to further study the characteristics of your assembly. All right. So since we are running out of time, let me quickly cover radiation and what things to consider when you specify radiation related study. So for this, I have chosen an example of a flashlight head. So here the assumption is it contains several components. There's an aluminum casing, and there's going to be a glass bulb inside, and there's going to be a reflector, and the front portion is covered by a glass cover. So what's going to happen is, as we told before, when there's a component which has a temperature above absolute zero, in this case the bulb's going to get heated up to a certain level, and it's going to emit radiation. So we want to find out how this radiation would dissipate through my assembly to the surrounding, and how will it cause the other components to heat up. So when it comes to radiation, it's quite important you understand how your assembly components would uh, dissipate this radiation out, whether it would absorb it completely or reflect it completely, or it would absorb certain amount of it and reflect the other percentage out. So this is purely decided by the material properties as well as the surface finish. So when it comes to a radiation absorption or reflection, there are two extremes: perfect reflector, which would dissipate out or reflect out all the radiation which it receives, and the other extreme is black body. So black bodies are supposed to absorb all the radiation which it radiation energy it receives. So this parameter can be input into your thermal analysis module when you do the setting up. So let's have a look at the setup itself. Let me go back to my assembly. Right, so here in this case we have an exploded view of the assembly, and setting up a radiation related thermal study is exactly the same as how we do a normal steady state analysis. But here the only thing in addition to the heat power we do is, for example, in this case I selected the bulb, the entire bulb. I'm specified there's going to be a certain amount of heat power, 50 watts, and then I have to specify the radiation properties. For the bulb itself, what I'm going to do is I'm going to select all the faces or the surrounding surfaces of the bulb, and I'm telling the software that it's having an emissivity value of 0.7. So a perfect reflector will have an emissivity value of 0, and a black body which absorbs all the radiation will have an emissivity value of 1. So in this case what I'm assuming is the material the bulb's made of, it's absorbing majority of the radiation. Therefore, I'm using a value of 0.7. So most of the time this information comes from engineering literature or experimental data, or you need to approximate it. So there's a button called open system. So what this checkbox does is it allows you to assume a certain amount of radiation is lost to the surrounding. It escapes the surrounding if it's an open system. But in our case, the bulb resides within a closed system. It's covered with this glass. So therefore, I'm not using that option. And there's another tool called surface to ambient. For example, if a certain amount of or all the radiation generated is lost to the surrounding or the ambient, you can use that option. So it's not applicable here. We'll be using it later. I'll show you. So the next is the reflector. So the reflector is supposed to reflect out majority of the radiation it receives. That's the purpose of it. So it has a shiny surface and it's made of aluminum. So what I'm going to type in here is a value which is closer to 0, which is closer to a perfect reflector. So that's typed in as well. Click OK to that. And finally, the inside surface of the glass cover, which is open to the internal components of the flashlight. So that is again going to absorb a majority of the radiation. So it's 0.97 emissivity value. And again, the last one is the outside surface of the glass cover, which is open to the surrounding. So here, this too has an emissivity value of, not sorry about that, not that. Yeah, that too has an emissivity value of 0.97, but in this case, I'm using a condition called surface to ambient. So what I'm assuming here is all the energy or the radiation which gets dissipated out of the surface is lost to the surrounding. It does not get absorbed by any other surface, which was the option used for other radiation conditions. And here, one more thing you have to specify is the ambient temperature, what's the surrounding temperature, and the view factor. So view factor is something which takes into account the possible obstructions present in front of your surface. For example, if this glass surface had a few more objects right in front of it, some walls or any other electronic components in front of it, which obstructs the path of radiation, then I have to use a value which is somewhat between 0 and 1. But if it's completely open to the surrounding, I could use a value of 1. All right. So again, just to highlight, in a flow simulation module, That too can calculate radiation dissipation. The good thing is it does calculate the V factor based on your solid geometry and the computational domain. But in our case, in SolidWorks simulation professional modules thermal analysis, you need to approximate the V factor based on your assembly surroundings. Okay, so here of course it's a very simple case. We are assuming there's nothing present in front of this surface, so therefore we can use a V factor of 1. All right. And also finally, I need to specify the convection properties. So basically, the glass cover is open to the surrounding, and I'm assuming there's going to be a certain amount of air flow which it experiences. Therefore, I'm using a convection coefficient of 70, and the back face of the reflector, that's open to an air domain as well. So I'm using a lower value of 50 watts per meter squared Kelvin. So here the assumption is that the both surfaces are undergoing two different rates of convection coefficients. The values I'm using here are obviously arbitrary, just to demonstrate to you the effect of convection and radiation separately. Right, so once you do the analysis, what you're going to get is a heat result, temperature result, purely due to the heat power and the radiation effects of it. So if you want to have a look at it better, so I'm going to hide the glass cover first, hit the tab key and reactivate the plot. And afterwards, what you can do is you can even find out the heat flux, which gives you an indication or a clear image of how well the heat gets reflected from certain locations and where most amount of heat gets accumulated. So based on it, you can improve your design. So that is about utilizing radiation in your thermal analysis. Right. So that's about it for the webinar today. So in the future, I'm hoping to cover another webinar which covers how to utilize flow simulation tools to analyze heat dissipation in your assembly and take into account fluid defects as well.